Good afternoon, ladies and gentlemen. Welcome to this INF 503 lecture. So today we're going to be talking about BLAST, Basic Local Search Alignment Tool algorithm. This is a heuristic fuzzy matching algorithm that is going to, in this class, represent a whole type of algorithm, which is called seed-based searching. So what we're going to do today is we're going to talk a little bit about the rationale for heuristic algorithms. Why should we use heuristic-based algorithms versus the exhaustive algorithms that we've talked about previously in the class? We're going to go over the actual details of the BLAST algorithm. How do you implement it? And then finally, we're going to talk a little bit about the time and space complexity of the algorithm and what would that give us for the problem that we're trying to resolve. Okay, so to ground us a little bit, let's remind us again of the problem that we've been solving in this class. So if you recall, what we're trying to do is we're trying to resolve a problem where we have a larger number of queries, big N. In our homework example, N is about 27 million. Each query is, for the sake of simplicity, is a fixed length. Let's say for the sake of argument, it's 36. And we're trying to find these queries inside of a subject, which big G, which in our example is about 3 billion characters long. Okay, so to date, we have considered several types of fuzzy matching algorithms. And recall, fuzzy matching algorithms are algorithms that allow us to find a query within a subject, even if there are some limited number of errors between the best match between the query and the subject. Okay. So the two algorithms that we've talked about so far, one is the Needleman-Wunsch algorithm. The Needleman-Wunsch algorithm is exhaustive, right? So, which is good because it gives us certain guarantee that we're going to find the best scoring match between our query and our subject, if one exists. So that's great. We have some guarantee of success. Needleman-Wunsch is a global alignment algorithm. Right? So it's going to seek to match all of the characters of sequence 1 against all of the characters for sequence 2. Okay? Finally, and this is going to be important, the search time for the Needleman-Wunsch algorithm for our problem where we have big N queries, each little n in length, searched against a subject of size G, is O of big N times O of little n squared times O of G, right? We're going to come back to this in a second. Now, this should all make sense to you because, again, we have big N queries. For every single one of those queries, we're going to generate a whole bunch of small matrices of little n squared matrices for every n-mer in our genome G. Okay, so the other algorithm that we've talked about is Smith-Waterman. So again, Smith-Waterman is an exhaustive algorithm, which again means that we have guarantee to find the best match. It is a local alignment algorithm, which means that it's going to find the best subset of G that matches whatever query that we give it, right? So you don't have to stretch all the characters of string one against all the characters of string two. And importantly, it does provide us with some speedups, right? In order to do the searching, it's big O of n, because that's how many queries we have. And we don't have to create a whole bunch of little matrices. We can just create one big matrix, right? So this would be big O of little n times G, right? Now, what is the problem with these types of algorithms? I mean, they're about as good as you can get from the point of accuracy. You are guaranteed to find the best scoring alignment if one exists, which is great, right? Anybody, whenever you're doing the search process, you want to be able to find the thing that you're looking for if it's there. The problem, of course, comes in with what are we paying for this guarantee of exhaustiveness, right? In our scenario for the homework assignment, big N is 27 million, little n is about 36, depending on the data set that we're using. And big G is 3 billion. Depending on the efficiency of your code, if you were to try to attempt to solve or search for all the queries in the genome of size G, and depending on your efficiency, it would take somewhere between 2,000 to 8,000 years. Right? On a single CPU, you would have to wait 2,000 to 8,000 years in order to complete this assignment, which is not great, right? Now, Smith-Waterman is better, right? Specifically O of little n better. So in this particular case, roughly a factor of 36 better. So if you were to try to solve our homework assignment with a Smith-Waterman approach, it wouldn't take you thousands of years, it would take you hundreds of years. Depending on your efficiency, somewhere in between 200 to 300 years. Now, again, 200 to 300 years is probably more time than you want to wait for to complete one homework assignment in one graduate level course in computer science, right? So exhaustive approaches are great in terms of accuracy, but not so great in terms of time. If your data set is large enough, they become prohibitively expensive and not feasible. Now, of course, you can speed things up by parallelizing some of these things, right? But the fact of the matter remains, it's going to be very, very computationally expensive for you to solve the problem the right way, right? So we're going to have to come up with some sort of a heuristic, some sort of a speed up, even if we lose the guarantee of exhaustiveness, to do better than this, right? So let's consider for a second, where is it that we are wasting most of our time, right? Let's talk about the Needleman-Wunsch approach. Now, let's say, for example, again, we have our big N queries, each little n in length, and big G in the genome. And let's say that we've taken our very first query, let's call it S1. And for the sake of argument, let's say that there is a near exact match to S1 here in this portion of the genome. And let's say there's 2 mismatches in that match. So the problem or the challenge that we want to avoid is, in the Needleman-Wunsch approach, we're going to take our query and we're going to compare it to the first n characters. And we're not going to find it. The answer is going to be terrible. It's not going to be a very good match, right? Because again, there is a match, it's over here. We've just wasted the computation to do Needleman-Wunsch on these first n characters. We're going to move it over by 1, and again, wasted effort. That's not where the thing that we're looking for is. Wasted effort, wasted effort. The problem with Needleman-Wunsch approach is in this term. We can't really do anything about O of n, so not a problem. This is not that big of a deal. It's only 36 by 36 matrix. The problem is in this term over here. G, if you remember, is about 3 billion. Assuming for a second, and it doesn't have to be the case, but assuming for a second there is one best location that S1 would be aligning to, we've just wasted about 3 billion times of us making O of n squared little matrix, right? So that's a problem. Now, let's say, for example, you go to, I don't know, the Library of Congress, right? And you're looking for a particular book, or any large library for that matter. If you're looking for a particular book, are you going to look at every single book one at a time to see if it's the book that you're looking for? No, that would be a terrible idea, right? You try to figure out roughly what genre of the book it is. Let's say it's science fiction, then you go into science fiction category. Then you're gonna hopefully know who the author of the book is. Then you're gonna go to all the authors that begin with that particular letter, and then you're gonna look around in a particular portion of the library for the book that you're looking for, right? That's how you save yourself from having to look at every single book at a time. What we're gonna try to do is the same idea, right? What I'm going to say, so let's say this is my G. A, T, C, A, G, T, C, A, G, T. Right? And let's say that the sequence that I'm looking for, the query that I have is TCATT. Right? Now, hopefully just by looking at it, you'll notice that it matches somewhere around here. Right? T is going to match with a T, C is going to match with a C, A is going to match with an A, T is going to mismatch, T is going to mismatch, right? Or alternatively, it could match somewhere over here. Again, T is going to mismatch. What I'm going to ask you to notice is that in the places where it matches, sequence 1 matches to G, there's certain subsequences that match perfectly, right? So TCA, for example, matches perfectly. Oops, pardon me. TCA matches perfectly over here. So the whole idea of the basic local search alignment tool is, if we're going to find a match between the query that we're looking for and some very large subject, right? It's going to have subsequences of our query are going to match perfectly, and some subsequences are going to match with errors. But there's going to be at least one, hopefully, that matches perfectly. Now, what data structure that we know of that would enable us to very quickly look for perfect matches? Right now, the quickest data structure that we know of in this class that looks for perfect matches is a hash table. Okay, so that's the central idea of the BLAST. So let's go through the implementation of the BLAST algorithm, and then hopefully you'll see how we're going to incorporate hash table based searching in order to greatly speed up what we're trying to do here. Again, so let's talk about the actual BLAST algorithm. BLAST incidentally stands for Basic Local Alignment Search Tool, right? It's just one example of something called a seed-based search. And we're going to talk about what is a seed. it is going to be heuristic. It's going to lose the guarantee of exhaustiveness. And hopefully what we get instead is a much faster algorithm. So let's talk about the steps. The steps are, we're going to break up the subject G into k-mers of a particular size, right? So step one, this is our subject G, into k-mers such that k is less than little n. Remember, little n is the size of our query, right? And we are going to store the location of each of these k-mers in the subject sequences in a hash table. Okay, so remember, for our example that we're trying to do here, the G is ATC, AGT, CAGT, right? And let's say for the sake of argument that K is equal to 3. So we're going to create every single possible 3-mer from G and store it in our hash table, right? So let's do this. We have ATC, TCA, CAG, AGT, GTC, TCA, CAG, and AGT. This one is on position 0, position 1, position 2, position 3, 4, 5, 6, and 7. Right? So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 characters. Good. Hopefully I have not missed anything. Okay, great. So we're going to store this in a hash table, your favorite chaining collision resolution hash table, or wherever you want to do it. Okay, great. So that's step one. So what we've done here is actually called indexing. We've indexed or chopped up our subject into smaller pieces and figure out exactly where each piece is, right? It's now in the hash table. We know the location. We know that ACT begins on position 0. We know that specifically TCA has 2 places and they are in position 1 and 5. So we recorded, indexed all of the k-mers in the entire sequence. Great. So step 2. We are going to repeat the process by breaking down the query into k-mers of the same size, storing the location of the query, right? Such that k is less than n. Remember, n is the size of the query. And store the location of each k-mer in the query. You can use a different hash table for this. You can store it in an array. That part doesn't really matter. Okay, so let's say again, our S1 is TCATT. Great. We're going to break it up into k-mers, and that's going to be TCA, CAT, and ATT. Okay, great. This is on position 0, position 1, position 2. Great. So now we have k-mers from the query, we have k-mers from the subject. The next step is going to be to search for the k-mers of the query in the k-mers of the subject. Okay, so again, these are the k-mers of the query, TCA on position 0, CAT on position 1, ATT on position 2, right? To remind us, let's look at all the k-mers of the subject. Does TCA exist in the subject? Yes, it does, right? It exists, it's in position 1 and in position 5. Great. Does CAT exist in the subject? No, it does not, right? So great, we have not found it. Does ATT exist in the subject? No, it does not. We have not found it, right? So what we have right now is we know that at least 3 characters of our queries match at around position 1 in the subject and around position 5 in the subject. These k-mers that match in position 1 and 5 are called seeds. The reason that they're called seeds is they're going to act as seeds for us, extending the alignment around that region of our subject, right? So, and that is exactly what we're going to do. So once we have 1 or more seeds, we are going to extend the seeds using local, or if you really want to, or global, alignment algorithm. So here's the idea. We now have 2 seeds, right? TCA, that's on location 1 and 5 in our genome. So on position 1, right here, TCA exists. Now, what we're going to do is we are going to go to the left and to the right of this position, however much we need to, in order to cut out a portion of our G to feed into our tool, right? If we're using a local search alignment tool, things are kind of easy, right? So I know my query is of size 5. I know it starts on position 1 in the subject. I know local search is good enough for finding what I'm looking for in a constrained location. So for local search, I can just say, hey, if I know my seed starts in position 1, I'm just going to take however long n is to the left and to the right of it, and I'm going to look in there. Great. That's one way to go about it. And that's the local way, right? So local, or essentially Smith-Waterman, we can just go plus or minus n from seed location. we're going to add, we're going to end up creating a matrix that is 2n by n. And hopefully find the thing that we're looking for in there. If we're trying to use a global approach, things are a little bit more complicated, but we are able to resolve things a little bit faster. So let's say, again, on position 1 here, I know that I have TCA because that's where my seed is, right? So how far to the left of the position 1 I'm going to go, and how far to the right of the position 1 I'm going to go. Well, I know that the TCA that I found is on position 1 in the subject, but position 0 in the query, right? So it's right here, the first 3 characters. So if it's in position 0 of the query, I know that I don't have to go at all to the left, right? I can just go 5 characters to the right and find the thing that I'm looking for. In this particular case, the match that I'm looking for. If I would have gotten one of these k-mers matched from position 1, I would know I'd need to go 1 character to the left of wherever it is my hit was for the seed in the subject, and then 4 characters to the right, and so on and so forth. Right? So global alignment. Or Needleman-Wunsch will require us to use location of seed in query to figure out cut location. Right? Again, let's do a little bit less abstract and take a look at the actual sequence, right? So our G was ATCA GT CA GT. And we found this TCA from our subject, TCA TT. Matched up. So what we're going to essentially do is say, hey, I found where it looks. I'm going to cut out 5 characters here, and I'm going to run a Needleman-Wunsch matrix TCA GT against TCA TT. And not surprisingly, I'm going to find that these 2 match, right? And I'm also found this guy right here. Again, TCA matches here. And I'm going to do the same thing. I'm going to cut out this portion of the subject and again do the Needleman-Wunsch. Okay, so this is the algorithm. The algorithm essentially break the query into smaller pieces, find perfect matches to the subsequences of that query, and then extend it using the exhaustive, fantastic algorithm that we have identified. Okay, great. So why is this approach here? So we're done with the algorithm. Why is this approach heuristic? Right? Let's say, for example, my subject is ATCAGTA, right? And my query that I'm trying to find is CAAT, right? You hopefully see that this CAAT will line up pretty well with this region of the subject. But let's say, for example, that my K is equal to 3. Let's see if my on-the-fly example worked. I'm going to have CAA, AAT. Those are going to be my 2 k-mers that I'm going to break up my subject into. Now, I'm going to argue that CAA is present nowhere in my G, right? There is no CAA. So I'm not going to find this seed to extend. Now, similarly, AAT is also not present in my G. So I'm not going to find this seed to extend. So the problem lies in the fact that if you don't find a proper seed, you will never know to start looking in a particular region, right? So that's the heuristic, right? You're not guaranteed to find the answer. So in this particular case, we can see that there's a one mismatch solution to the problem, but we're unable to find it because all of our seeds are broken. There is no 3-mer match in subject G in the query that we're looking for. Okay, great. So it's a heuristic approach. There's a possibility that you're not going to find the thing that you're looking for. That's not great. Did we at least get a sufficiently fast speed up to the problem, right? Remember, the times that we have to beat the Needleman-Wunsch search time is O of big N times O of N squared times O of G. And then the search time for the Smith-Waterman is O of N times O of N times G. Those are times to beat, right? So let's do quick back of the envelope calculation of what would be the search time in a seed-based basic local search alignment tool, right? So search for BLAST. So we still have big O of N queries. We're not getting away from that. We still have to do it one query at a time, right? How long is it going to take us to search for the k-mers of the subject? K-mers of the query in the subject. Well, if we're using a hash table and it's a properly set up hash table, right? So you don't, you're not getting into the really bad search time. I'm going to argue that it's going to take me O of constant time to do the actual search, right? O of C is how long it takes for me to search for something in the hash table. Now, I did have to break down the query into k-mers, and I'm going to have approximately O of little n k-mers, but this is how long it's going to take me to search for seeds. Okay. How long is it going to take me to actually do the local search alignment? Right. Let's say for the sake of argument, we are using Needleman-Wunsch, right? It's going to take me approximately O of N squared to do that once I found my seed, right? So in BLAST is going to be O of N times O of N cubed. Is this better than the previous examples that we had? Well, I'm going to argue that if G is significantly better or significantly larger than N, which it is, in our case, little n is 36, big G is 3 billion. We're going to have significant speedups, right? So specifically, while moving from a Needleman-Wunsch to Smith-Waterman algorithm gave us approximately 36x speedup. Moving from Needleman-Wunsch to BLAST gives us 3 billion divided by 36. So hundreds of millions or tens of millions times speed up, right? So going from here to here is millions of times faster, right? And that's an important component, right? We lost the exhaustiveness, right? We could make a mistake. If our seed is too long, the longer the seed, the shorter the search time is going to be, right? Worst case scenario, if my seed is of size 1, BLAST becomes essentially a Needleman-Wunsch, right? But if my seed is longer, I'm going to require more of my query to hit before I start looking for it, right? So the longer the seed, the shorter the time, but the shorter the time, the less accurate my search is going to be. So essentially it's a trade-off between time and speed. Okay, so to recap, we have a brand new type of algorithm. It is a basic local search alignment tool, which is an example of a seed-based algorithm. And the central idea in the seed-based algorithm is we break the query and the subject up into smaller subsequences, k-mers. We do perfect searching, which is very fast. And then we only do the expensive O of little n squared Needleman-Wunsch or Smith-Waterman algorithm when we're pretty darn sure that we're going to find what we're looking for. Okay? Heuristic, millions of times faster than the exhaustive approach. So if you were to try to do the homework assignment using basic local search alignment tool, which you will, it will actually be finished in a matter of hours rather than hundreds of years, which is a big deal. Okay. With that, thank you for listening and have a wonderful day.